Hello and welcome to the third lecture on dynamics of structures. We are continuing with the multi-degree of freedom systems. In this lecture, we will be talking about the study of natural frequencies and natural modes of vibration. And next, we will be talking about the free vibration response of systems. So starting with the equation of motion for the multi-degree of freedom systems, we know that the equation of motion for the multi-degree of freedom systems can be resembled in terms of matrices. Now that can be put as mu double dot plus ku equal to 0. Now once we know this, for any particular pt equal to 0, this is number one, this is without damping, and number two, it's without load. So this is a free vibration condition that we are talking about. Now there may be certain initial conditions for the motion, and the initial conditions, let us assume that they are u is equal to u naught and u dot is equal to u naught dot at t is equal to 0. Now this, the above equation, the matrix equation resembles a differential equation, n homogeneous differential equations that are all coupled up through mass matrix, the stiffness matrix, and both the matrices, and n is the number of degrees of freedom that we have in a multi-degree of freedom system. Now when we are talking about the general procedure to obtain the desired solution for multi-degree of freedom systems, which we talked about in the earlier lectures, what we got is that there are various methods of representing the solution, and one such method could be the graphical form that enables us to understand the free vibration of a multi-degree of freedom system in qualitative terms. Now here is given a figure, and this figure is of it's a two-story shear frame. The story stiffnesses and the lumped masses at the floors can be seen, and the free vibration is initiated by the deflection curve A, which shown in B part here. Now there is absolutely no force acting on the system, it's under free vibration, while as A is the curve, the deflection curve, under which the free vibration is initiated. Now the resultant motion that happens, which is uf of the two masses, that's m1 and m2, which is here 2m and m, that can be plotted in terms of time, and that's been plotted in D part here, where t1 will be the time period of motion. Now the deflected shape here of the structure at any instant of time, there are three deflected shapes given here, A, B and C. The Qn has been plotted here in the C part, and what is this? This is the overall force vibration of the system. Now if we see that the displacement and the time plot for any floor, say for example for any jth floor, if it starts with uj0 and uj dot 0, then in the uj0 are identified here in the B part. Now what is that? u1 and u2 0, these are being identified here as the initial displacement conditions. Now what we observed earlier for single degree of freedom systems, there we observed that the mass, the motion of the mass is not simple harmonic, and the frequency of the motion cannot be defined. Furthermore, the deflected shape, the ratio u1 by u2, varies with time, as is evident from the differing deflected shape B and C, which are in turn different from the initial deflected shape A. Now an undamped structure would undergo simple harmonic motion without change of deflected shape. However, if free vibration is initiated by appropriate distributions of displacements in the various degrees of freedom, as shown here in the above figure, what we can get is that there could be two characteristic deflected shapes that exist for this 2 degree of freedom system. Let me try to explain it in this terms, that if there was a single degree of freedom system, then there would be a single degree of a deflected shape. But for a two degree of freedom system, there could be a multiple ways in which, or modes in which, it could deflect. Now we can say that there are n number of modes for any system which is vibrating. Now what does n depend on? N depends on the number of degrees of freedom. So there is always a particular node, and there is always a particular mode of the motion of the motion of the structure or the system. There are two modes of vibration that would be acting on this system. Number one, the first mode of vibration that's given here in this figure. You can see in this figure that it's the first mode of vibration has opposite ends of deflection. In this mode of vibration, one can see that the first mode is always resembled as phi n1, and where n is the number of modes and number of degrees of freedom of the system. Now phi 11 will be the mode of vibration at the first story level, and phi 21 will be the mode of vibration at the second story level. This is just a graphical representation of the deflection. So when we have such a mode of vibration, we can see that the node here is concentrated at the ground floor level. When the node is concentrated at the ground floor level, it's clear that it's the first mode of vibration, and it's known as the natural mode of vibration of a multi-degree of freedom system. Now if the deflections are plotted, and we can observe in the figure D here that the deflections at time instants A, B, C, D and E, these are different time instants during the mode of vibration. We can see that we can resemble the different modes of vibration and the deflections at different time periods during one period of one period cycle of the vibration. The modal coordinates that are the first modal coordinate q1t is given in figure C, and one can see that there is no damping happening here, and the deflections are starting from an extreme end. So because the initial displacement was equal to u naught t, thereby now here we have a certain time period t1, 2t1 and 3t1 given in figure D, where t1 is 2 pi by omega 1. What we have seen is that when there is a natural mode of vibration, the extreme displacements at the same time, and they pass through the equilibrium position also at the same time. Now here the equilibrium positions would be same as where the node is located. Now in the first mode of vibration, we saw that the motion was of both the floors was in the same direction, but then it will be in opposite direction when it comes to the second mode of vibration. The point of zero displacement, which is here the node, does not move at all. As the modal number n increases, the number of nodes also increases accordingly. So thereby in the first mode there was no node acting anywhere apart from a central node acting at the ground floor level. And in the second mode of vibration, there is an additional node which is acting here, and we call this as the first node acting at the first above the first story level. Now what does this have to do with the modes of vibration? The nodes give us an idea about the point at which there will be no static displacements at all, and thereby we can locate such nodes in the columns. Once we locate such nodes in the columns of a structure, we can tell the maximum impact of the displacements during an earthquake or any other particular phenomena. Now we can say that the natural period of vibration Tn, which is given in the figures above, of a multi-degree of freedom system, it's a time required for one cycle of the simple harmonic motion in one of these natural modes. Now, the natural period of vibration would be for the first mode it would be T1, and for subsequent modes it could be taken as T2, depending upon the natural circular frequency of vibration, which is omega n. Now we know that the natural cyclic we know that the natural circular frequency omega n for any particular motion is given as under root of k by m. Now we can then here are given that Tn is 2 pi by omega n, and Fn, which is the natural cyclic frequency, it's 1 by Tn, whereas omega n is 2 pi by Tn. Now we have seen that there are two natural modes here, phi 1 1 corresponding to the first mode of vibration, phi n1 corresponding to first mode of vibration, wherein we had at two story levels we had two deflected shapes, phi 1 1 and phi 2 1 for the first mode of vibration. For the second mode of vibration, we saw that at the first floor level it was phi 1 2, and at the second story level it was phi 2 2. Thereby we can say that the natural modes of vibration that occur for a particular story can be resembled in terms of modal deflections, and it can be graphically represented. But all graphical representations could be transferred into a matrix form, wherein the matrices would give us the amount of deflections that could happen, and this is known as a modal shape. Now, what is a modal shape? A modal shape for the first mode we saw was a corresponding graph which looked like bending on either side of the particular motion. For the second mode, for the first floor and the second floor, it was bending on the different sides. So for the extreme position, when t is actually equal to for the extreme position, when t is equal to e here in this figure, one can see that the modal shape given to us is completely opposite for the first and the second floor. Thereby we can write down the modal shape in terms of phi n equal to phi 1 n, phi 2 n. Now this modal shape will be quite important because we can relate it with other parameters to be discussed later. Now we would be talking about the development of the eigenvalue problem for the natural frequencies and the modes of vibration of the system. Now we have already seen that for an undamped system, the free vibration in any of the natural vibration modes was graphically depicted, as we saw in the figures earlier. Now that could be mathematically described. And how could we describe that? We could describe the displacement as equal to qnt into phi n. Now what is qnt and what is phi n? Phi n is a particular modal shape. For example, in the first modal shape, what we saw that in the first mode, phi n was equal to phi n1 and phi 2n. It was phi 1 1 and phi 2 1. And for the second modal shape, it was phi 1 2 and phi 2 2. Now this is the modal shape for a particular mode. N, qn is the displacement. Now this is the displacement for a modal coordinate, the amount of displacement. So we can say this is the maximum amplitude that we can obtain from qn for a particular mode. For example, in the earlier figure we saw qn was a modal coordinate wherein it gave the maximum and the minimum amplitude at particular instants of time. Thereby, we can relate with this Qn the total displacement ut. Now, you would be confused at this particular moment of time. How do we define the modal shape, and how do we define Qn? Qn, as you saw in the figure, it's being defined in terms of maximum 1 and minimum -1. So it's a normalized value. While as multiplying by the modal shape, you will get the overall value of displacement, right? Thereby, now we can say that the time variation of displacement Qn, which is known to us, how can we relate it? We can relate it with an cos omega nt plus bn sin omega nt. Why? If you have the look at the figure, it is the condition of the free vibration, and we have already resolved this in single degree of freedom systems. So what we have actually done is that we have now resolved UTN in terms of the single degree of freedom system by just multiplying the modal shape at particular locations to the values that we obtain from the single degree of freedom systems. Now A and Bn here are known, they are the constants of integration, and that can be determined from the initial conditions that initiate the motion. Now once we combine these two equations, first equation ut equal to qnt phi n, and the other equation qn equal to an cos omega nt plus bn sin omega nt, what we get is that ut is equal to phi n into an cos omega nt plus bn sin omega nt. Now two parameters omega n and phi n are both unknown here. They are both unknown here. We don't know the natural frequency for individual particular modes of vibration, and we do not know the modal shapes. Unless and until we don't get them, we will not be able to solve for ut. Now we are going to substitute the value of ut in the equation of motion mu double dot plus ku equal to 0. What we get is minus omega n square m phi n plus k phi n into qnt equal to 0. Once we have obtained this form of the equation, this is quite a useful condition wherein we can now determine the value of the values of qn and phi n. So we can determine the value of the modal shapes. Now there are two conditions. Either qnt would be equal to 0, which would imply that ut is equal to 0 and there is no motion happening of the system. That would be a trivial solution and that cannot be possible. Then the other condition is that minus omega n square m phi n plus k phi n is equal to 0. If we take this condition, then k phi n would be equal to omega square n square m phi n. Now here the natural frequency is omega n and the modes are phi n. Now this is an algebraic condition wherein the matrix eigenvalue problem can now be solved. Now we all remembered what is the eigenvalue problem. The eigenvalue problem is A is equal to lambda into I. Thereby here this equation could be taken in terms of an eigenvalue condition. When it's necessary, it is called the real eigenvalue problem to distinguish it from the complex eigenvalue problem that we have mentioned earlier for systems which include damping. There are two matrices here in this equation, k phi n equal to omega n square m phi n. One of the matrix is stiffness matrix, that's K, and the other matrix is mass matrix, that's M. Now the problem is to determine the value of the scalar product here, which is omega n square, and of the modal shape phi n, which is in the vector form. Now what would be the solution for this? That could be obtained only when we take the matrix of K minus omega n square m into phi n equal to 0. Now once that is done, what we get is that this can be interpreted as a set of n homogeneous algebraic equations for any n number of elements, where phi n would be varying from phi n would have solutions from 1 to n. This set always has a trivial solution wherein phi n would be 0, but it's not useful, and it implies that ut is equal to 0, and it implies that there is no motion. The only non-trivial solution that we could have for this condition, K minus omega n square m into phi n equal to 0, is that once the determinant of this matrix K minus omega n square m is equal to 0. When the determinant of this is 0, we get a polynomial of order n in omega n square. Thereby the equation here, which is the determinant of K minus omega n square m, is known as the characteristic equation or the frequency equation. Now this equation, as I told you, has n real and positive roots for omega n square, because m and k, both the structural mass and the structural stiffness matrices, they are both symmetric and they are both positive definite. This property of being the positive definite of K, it's assured for all the structures in a way that prevents rigid body motion. Thereby what we get is now n values of omega n square, and they are all real and they are all positive. So the positive definite property also exists for m, the mass, and that is known to us because there is a lumped mass for all degrees of freedom which are non-zero, and thereby in the analysis after the degrees of freedom with zero lumped mass that have been eliminated, as earlier we stated in the static condensation in the earlier lecture, we stated once we eliminated all the degrees of freedom by the static condensation method, the n roots that we are getting for omega n square, we can now get n natural frequencies omega n of the vibration. Now these roots of the characteristic equation, determinant of K minus omega n square m equal to 0, they are known as eigenvalues, and they are known as characteristic values or normal values. When a natural frequency omega n is known to us, now we can solve the equation K minus omega square m into phi n equal to 0, the matrix form, into scalar product phi n equal to 0. We can, the K minus omega n square m, the matrix form, into vector product phi n equal to 0. We can solve this, and what we can obtain after solving this are the values of phi n. Now phi n would mean that we are now getting the values of modal shape. Thereby the eigenvalue problem, although it does not fix the absolute amplitude of the vector phi n, but what it gives us, it gives us the shape of the vector. And once we know the shape of the vector, that is obtained by relative values of n number of displacements that we are getting from phi n, corresponding to n natural vibration frequencies omega n of a n degree of freedom system, there would be n independent phi n's, which are all known as natural modes of vibration or natural mode shapes of vibration. These vectors are known as eigenvectors or characteristic vectors or normal modes. The first thereby the first modal shape would give us the first normal mode. In summary, what we are getting is that we are getting a vibrating system with n number of degrees of freedom, which has n natural vibration frequencies omega n arranged in a sequence from smallest to largest. Now, omega 1 would be always less than omega 2 and it would be less than omega 3 up till the omega n being the largest, and they correspond to the natural periods Tn and the natural modes phi n. The term natural is used to qualify that each of these vibration properties that we are emphasizing, that there are natural properties of the structure in free vibration, and they depend on two things, mass and stiffness. That's why it's called as a natural property. The subscript n denotes the mode number, and the first mode n is equal to 1 is always known as the fundamental mode. Thereby, in summarizing, what we have got is that omega 1 is the least natural frequency, circular frequency, and Tn is the natural period of vibration, and phi n are the natural modes, while as phi 1 is the fundamental mode or the first mode of vibration. Now it's known to us that there are n number of eigenvalues and there are n number of natural modes that are obtained from the equation that we have got, the characteristic equations. Now, modal shapes with respect to each of the modal nodes or modal values is, for example, for the first modal or the fundamental mode, the modal shapes that we have are phi 1 1, phi 2 1, etc. up till phi n1. Similarly, for the second modal shape, the modal values are phi 1 2, phi 2 2 up till phi n2. Thereby, we can club the modal n number of modal eigenvectors into a single square matrix, and here each column is a natural mode. Thereby, and here is given a matrix of phi equal to phi jn equal to phi 1 1, phi 2 1. This is the first column up till phi n1, and similarly there are other columns. Now each column here represents a particular natural mode phi n, and it's corresponding to a particular natural frequency omega n. Thereby, the number of elements that we have here are phi jn. Next comes the matrix phi that we have obtained here, which is the modal matrix. Now it's known as the modal matrix for the eigenvalue problem. There are n number of eigenvalues of omega n square, and they can all be clubbed into a diagonal matrix, and it's resembled by ohm square, where which is known as the spectral matrix of the eigenvalue problem. It's given here. Now this is a diagonal matrix, and what we can know from here is that the value of omega 1 square corresponds to the modal shape phi 1 1 up till phi n1. Similarly, omega 2 square corresponds to modal shape phi 1 2 up till phi n2, and omega n square corresponds to modal shape phi 1 n up till phi nn. And how have we obtained these values, omega square values? These have been obtained for each particular modal shape from the eigenvalue problem or the characteristic equation that we have earlier developed. Now, what is the reason of putting this into the matrices form, both the modal matrix and the spectral matrix? The modal matrix, which gives us the vectors arranged into matrices, the spectral matrix gives us the scalar quantities arranged into matrix. The only reason that is uh, for putting this or assembling this compactly into matrices is that we can display it as a single square matrix, and we can then resemble this complex system into much simpler system, wherein we can say that now k phi n is m phi n omega n square. Now again here, because we know omega n square is a scalar product, now therefore for n number of values of modal values ranging from 1 to n, we can arrange it into a modal and spectral matrix relationship, which is given as k phi equal to m phi ohm square. Now this is a compact presentation of the equations that are all related to the eigenvalues and eigen systems. Having now determined the modal matrices and the spectral matrices, next we are concerned with orthogonality of modes. Now what is orthogonality? When we are talking about linear algebra, an orthogonal matrix, it's a square matrix whose both columns as well as rows are orthogonal unit vectors or orthonormal vectors. So we can say that the transpose of a particular square matrix into that square matrix is itself equal to an identity matrix, or there could be an equivalent characterization where we can say that a matrix, for example A, is orthogonal if its transpose is equal to its inverse. That means A transpose is equal to A inverse, where A inverse is the inverse of Q. Sorry, A inverse is the inverse of A. Now, an orthogonal matrix is necessarily invertible, that is, A inverse is equal to A transpose. It's also and could be taken as unitary. Now, we would not be talking much about this property and its meaning, but we would be concerned with developing the orthogonality of the modes. Now we know here that phi and t, the natural modes corresponding to the different natural frequencies, they can be shown to satisfy the following orthogonal condition, which is given here in this figure: phi n transpose k phi r is equal to 0, and the other condition phi n transpose m phi r is equal to 0. This occurs when omega n is not equal to omega r. When omega n would be equal to omega r, then it would be a diagonal element that we are talking about. These important properties that we have shown here, these are the orthogonal properties. Now we need to solve these or prove these properties, whether the modes both K matrix as well as M matrix, that's mass and stiffness matrix, both are orthogonal or not. The way to solve this is, first let us take the equation that we already know, that is k phi n is equal to omega n square m into phi n. Now once we pre-multiply this, the equation that we have just discussed, it's known to us. Once we pre-multiply it by phi r transpose, what we get is the equation phi r transpose k phi n equal to omega n square phi r transpose m phi n. Now for any other frequency, rth frequency, k phi r would be omega r square m phi r. This is the characteristic equation that we are talking about. Now here we would be pre-multiplying it by phi and transpose. Once we do that, what we get is phi and transpose k phi r is equal to omega r square phi and transpose m phi r. Now from two equations, the first one obtained above, phi r transpose k phi n equal to omega n square phi r transpose m phi n, and the other one phi n transpose k phi r equal to omega r square phi n transpose m phi r. What we are getting is the following equation: phi n transpose k phi r, phi n transpose k phi r would be equal to omega n square phi n transpose m phi r. This is what we are getting from these two equations. Thereby, once we know this equation, we can, because we have utilized here the symmetry property of mass and stiffness matrix, and we have taken the transpose of the matrix on the left side of the first equation. It would be equal to the transpose of the matrix on the right side of the equation. Thereby, what we can obtain once we have this final equation, phi n transpose k phi r equal to omega n square phi n transpose m phi r. If we subtract the equation that we have obtained, the second equation, from the third equation that we have obtained, what we can get is omega n square minus omega r square into phi n transpose m phi r would be equal to, what would be the left side of the subtracting third equation to the second equation? It would be phi n transpose k phi r minus phi n transpose k phi r, that would be equal to 0. Thus what we get is we can from here determine the properties of omega n. Now it's clear here, this equation would be only true when omega n square is not equal to omega r square. Otherwise both the sides would be equal to 0, and thereby omega n is not equal to omega r, because we are taking the positive natural frequencies. And once we have these, we can get, this is a proof of the orthogonality relationship, that phi n transpose m phi r is actually equal to 0. Now that gives us the proof that the modal vectors are actually orthogonal, and both for mass as well as for stiffness. Having established this relationship of the orthogonality between modes with distinct frequencies where omega n is not equal to omega r, what we can get is that if there are j-fold multiple roots, that is, the system has one frequency repeated j times, it's always possible to find j modes associated with the frequency that we have satisfied in the first equation, which was phi n transpose k phi r equal to 0, which was the first condition of the slide. If these j modes are included with the modes corresponding to the other frequencies, what we get is just n number of modes which satisfy this equation for n not equal to r. Having determined this, the orthogonality of the natural modes implies that the square matrices are all diagonal. Thereby phi n transpose k phi would be proportional to k. K will be a scalar quantity. Similarly, phi transpose m phi would be equal to proportional to m, where again m would be a scalar quantity. Now the diagonal elements of both k and m are positive, and they are related by kn is equal to omega n square into mn, and know that Kn is equal to phi n transpose K phi n, and Mn is equal to phi n transpose M phi n. Now what are Kn and Mn? These are the diagonal elements of the matrices. And what is K, the capital K, the diagonal element of which are scalar? What is capital K and what is M? These are the modal mass. M is the modal mass and K is the modal stiffness. So what we have obtained from the orthogonality relationship is the modal mass and the modal stiffness. The modal mass corresponds to a particular mode and the modal stiffness corresponds to a particular stiffness. Now, although this can be demonstrated further, we will be now the diagonal elements of K and M are both positive. So Kn, we can say it's omega n square M. What we get after substituting in K phi n equal to omega n square M phi n, which is the characteristic equation, what we are getting is Kn would be equal to phi n transpose. Now the value of omega n square M phi n, which is the value of K phi n, because we know Kn is actually equal to phi n transpose K phi n. Now we have substituted the value of K phi n equal to omega n square M omega phi n here. Thereby Kn would be further equal to omega n square, we are taking out the scalar value, into phi n transpose M phi n. Now what is phi n transpose M phi n? It's the modal mass Mn. So it will be equal to Kn would be further equal to omega n square into modal mass Mn. Finally, we are going to discuss the normalization of modes. Now, what is the normalization of any matrix or any value? What we do is that we usually divide that element by the determinant of the matrix. If we are talking about the normalization of a matrix, so what we get is that we get the value in terms of we get all the values in terms of the normalized one value. Thereby we are actually determining all other here in this case we are determining all other modes in terms of a single fundamental mode. Thereby, if for example the value of the fundamental mode is 1, the value of the any other mode would be greater or less than 1, but it would be in terms of the fundamental mode. To do the normalization of mode, what we need to know is that if there is a vector phi n, which is the natural mode, any vector proportional to phi n, it's essentially the same natural mode as it satisfies our characteristic equation. The scale factors are sometimes applied to normalize modes to standardize their elements associated with various degrees of freedom. This process of normalization, it's quite convenient to normalize each mode so that its largest element is always unity. Other times it may be advantageous to normalize each mode so that the element corresponding to a particular degree of freedom, say the top floor of a multi-story building, is unity. In such discussions, what we come to know is that it's common to normalize modes so that Mn, that's the modal mass, have unit values. Thereby, in Mn would be phi n transpose M phi n would be a normalized I value. Whereas what we get phi transpose M phi would be an identity matrix I. It would be a diagonal matrix with unit values along the main diagonal. And from this, what we come to know is that the normal modes are not orthogonal but are normalized with respect to M. The natural modes are not orthogonal but are normalized with respect to M. That's the mass. They are then called as mass orthonormal sets. When the modes are normalized in such a manner as we have seen here, what we get from the earlier equations is that we know that Kn is equal to phi n transpose K phi n. Now, what would be the value of phi n transpose m phi n? That would be m n. Thereby, Kn would be omega n square m n. That would be equal to omega n square, because m n is an identity matrix. Thereby, K would be equal to phi transpose K phi would be equal to ohm square. Now we have normalized the system in terms of Kn being equal to omega n square and the modal stiffness K being equal to ohm square. Thereby the generalization becomes much more simpler.